So that means what? That means what we need to do is to figure out that what makes cosine KL/2 to be 0. Now we know that when cosine is pi/2 or negative pi/2, you're going to get 0, right? Therefore, we know that the value of k/2 equals to n times pi/2. And here, n will be any odd numbers. Would you agree? Now, the minimum root is this. If we let n to be 1, that means that's the first root. Therefore, we have KL/2 equals pi/2. And of course, that means k times L equals pi. And we know that by definition, k is equals to the square root of P/EI. You remember that's a definition we have where? Let's go back to here. We said that k squared equals P/EI, so k equals to the square root of P/EI, right? So by this definition, we're going to substitute it back here. Replace this expression of k with its definition. And then you're going to have this. Square root of P/EI, that's the definition of k, equals to pi/L. We just move capital L from the left-hand side to the right-hand side. Would you agree? And then we have found our critical low. P equals PCR, which equals to pi squared times EI over L squared. So this is how in your steel structures, why the expression of pi squared EI times L squared, why you are provided with this value. That's because of all these calculations that I just did. So this is the critical load. So we have found the critical load. Sometimes you call it buckling load. Of the structure. Now here, the key condition that we use in finding this critical load is this, in this problem, is to let the deflection approach to infinity. Remember I said last week, I said there are 3 different conditions we can use in finding the critical load. One of them is to let the deflection to approach to infinity. And the second condition is to let the stiffness to become 0. And the third condition is to set the determinant of the stiffness matrix to become 0. There are 3 conditions, and we just use 1 today. Okay, any other questions on this one? Okay, now let's go back to the PowerPoint. Let me see where did I stop here? Okay, so we talk about this and we talk about that. Okay, we talk about this and we talk about this example like this. And we talk about approaches and we're back to, okay, now we finished this one and we're going to continue with the next example. And this will be example, this example 3. The next example is to study the buckling load to determine the buckling load of a spring bar system subjected to an axial force. Now, we're going to come back to the note, which is here. This is going to be page 11 on my note. Not 11, 12. And the example number is going to be example 3. Okay. So what is this example? The example is this. If we consider a spring bar system, and that means there's a bar and it's connected to the support like this. This bar is subjected to an axial force right here, force P. And if we define this point to be A, this point to be B, and the total span is L, and also has its own E and I. And so where's the spring? We suppose that there is a rotational spring at point A, which at the support A. That means this is a rotational spring. And the rotational spring constant is K sub S. So here, I'm going to demonstrate you how we can use different approaches to analyze the buckling load from this simple example. The first one, our objective is this, is to find PCR. So in step 1, we're going to use the force approach. In the force approach, what we do is to define the free body diagram. So the free body diagram of this member. Now, before we continue, we're going to simplify the problem by assuming that this member, AB, is rigid, which means that it will not bend. But because there is a rotational spring, so the system is still stable. Because rotational spring will bring this column back to its neutral position. So we will take a one free body diagram by considering the following deformation scenario. That means, suppose the column deflects like this from the neutral axis, which means that from here to here, this angle theta. The force still acting here. This is P. And to balance this, of course, you also have internal action P at here, right? Now, what other forces we should consider in this free body diagram? Because there's a rotational spring. So when you produce this kind of deformation profile, there is going to be an internal bending moment which acting in this direction, correct? Trying to bring the rotated column back to its neutral position. So that's the internal moment. And this internal moment has a magnitude to be what? Because we said that this rotational spring is characterized by a spring constant Ks. So the moment equals to the spring constant times the rotation angle, correct? So this moment is nothing but just Ks times theta. what we have to do is just to bring everything to the moment equilibrium expression. So summation of all the moments should be 0. And you can choose whatever direction you like. Suppose we choose clockwise to be positive direction for the moment. And here, what do we have? The first term, you may use the internal moment, that's just Ks times theta. And what about the moment produced by this P? Now we know the magnitude of the force, but do we know the force arm? How do we determine that? The question is, what is this distance here, right? Yes. Any suggestions?
The L times the sine of theta.
Very good. L times sine theta. This is L times sine theta. Correct? And what about the moment? Is the moment produced by positive or negative? Positive or negative?
I can't say.
I mean negative.
Negative, because we already defined that clockwise is the positive direction here, right? And we are taking moment, of course, if I wasn't clear, we are taking the moment with respect to point A. So the moment produced by this force, denoted by the red arrow, P, is going to be negative. So that's going to become minus P times L times sine theta to be 0. Correct? Now, let's find out the expression of this force P. What will be the expression of force P? Simply, you just move the terms L over L times sine theta from one side to the other side, and this will become Ks times theta divided by L times sine theta, right? That's just the, this is derived result by rearranging terms. Okay. Now, one important assumption that we're going to make in this analysis is what we call the small deflection assumption.